All right, we're going to go through the rest of this note sheet. So we're going to talk about polynomial functions and sort of the basic vocabulary that we're going to be using this unit. We have some different polynomial functions down here, and we're asked to identify the terms, coefficients, and degree of the following polynomial functions, and to classify them with a special term if there is one. All right, so how this works, here we have the terms here. We just list them out: x squared, 5x, 2. Terms are basically the pieces of a polynomial separated by pluses or minuses, basically. All right, and then the coefficients here, well, even though it's not written down, we have a coefficient in front of this first term here. So we'd write 1, 5, and 2. Those are the coefficients of the different terms there. How we classify this is what we studied last unit. This is a quadratic. So we would call this a quadratic. Leave a little space there. The actual degree of this polynomial is 2, okay, or it has it's a second degree polynomial, but it has a special name, quadratic. All right, let's look at the next one. So, similar deal. Of course, we consider the terms with minuses in front of them. We consider them negative. Coefficients here would be 7, -2, and -1. The degree of this one is 3. Now, how am I getting this degree here? The degree is the highest exponent on a variable. Okay, it's not always the first term. Very often it is, but we're looking for the highest exponent on the independent variable, which in this case is x. So 3 is the degree. This one has a special name, which you should have seen on the last video, the graphs of cubic. Okay, so this is called a cubic polynomial function. All right, next one. The terms, well, really I should have written a little smaller here. I'm going to do this because I'm going to run out of room otherwise. Okay, those are the terms. Coefficients: 6, 4, -8, 1, because of course it's not written down, and 9. This is considered a coefficient. You might have wondered, wait, that's not a coefficient, it's not in front of a variable. Well, oftentimes we do consider it a coefficient. We might talk more about that later. We can think of it as the coefficient of x to the 0. Okay, just really quick. I don't want to get into too much detail here. But yeah, we have x to the 4th, x to the 3rd, x to the 2nd. This is x to the 1st. You can think of a constant as being the coefficient of x to the 0 power. All right. More on that later. So the degree here is 4. This does have a special name also. These are called quartics. Okay, so this is a quartic function. All right, next one, x to the 5th, -7 are the terms. Coefficients are 1 and -7. The degree is 5. These do have a special name too, called quintics. All right, and last but not least, we have this one. By the way, quintic is the last one we're going to use a special name for. There are other special names, but we're not going to get into that. So at this point, like this is has the degree of 8. Well, let me write down the terms and the coefficients. Okay, and then the degree here is 8, and it doesn't really have a special name, so we would just call this an 8th degree polynomial, which I didn't leave enough room to write that, but okay. All right, so that's how that works. All right, so these polynomials up in this table, they're all written in standard form. Okay, basically we have they're arranged in descending order of exponents. The term with the highest exponent comes first, then the next highest exponent, next highest, etc. All right, and then the constant is at the end. So where we just have terms being added or subtracted, that's standard form. There's also another form that we see with polynomials called factored form, and here's sort of the general setup, but here's an example of one if this is a little confusing. So here we have f of x times x plus 3 times x plus 1 times x minus 2. We could have a number out front here, a coefficient in front of all of this. We call that a. These are always just x's here, and we might have some constants in here also. We'll also see some later that we could have exponents on the parentheses too. We'll see that a little bit later. All right. So we need to write down the x values of the x-intercepts here. One thing to notice here, this is in factored form. This is also, and I'll mention this later too, but I think this would be a good time to talk about it. This is called sometimes intercept form because basically the x-intercepts are the same as these constants here in each set of parentheses. We would call each of these a binomial in each binomial. So looking at the x-intercepts here, we have -3, -1, and 2. I misspoke earlier. They're actually the opposites of these. These are not the x-intercepts. It's actually the opposites of those. We'll talk about why that is soon. The constants in the function are 3, 1, and -2. All right, moving on to the next, the other side here. Yeah, why do they have opposite signs? You might already know this. This came up in quadratics also. If you plug in the opposite, so like, let me write the original function here. That's going to be helpful to see. So we had x plus 3 times x plus 1 times x plus 2. If you plug in -3, which I have shown here, well, this is going to turn out to be 0, and it's going to make the whole thing 0, which, of course, when a function equals 0, it's going to be located on the x-axis. Okay, so where f of x is 0, or y equals 0, where's that located on any graph? On the x-axis. Okay, and that's going to happen with the other ones also. So I'll write these down. Oops, this should have been -2 up here. All right, so as we can see, when we put each of those in, -3, each of the zeros or the x values of the x-intercepts, we end up with getting 0, and it ends up on the x-axis. All right, so I called those zeros, which we mentioned that last unit a little bit. So this might be a little bit of review here. So x-intercepts, these were the x-intercepts for that last problem. The x values of the x-intercepts, well, this one's -3, and that's the 0 there too. Okay, so all right. So conclusion here: the x values of the x-intercepts of a function are simply called zeros. So we've talked about that before, but just wanted to mention it here. We're going to see that a lot this unit. All right, and on to the last part here, identifying the degree of a polynomial. So we talked about degree back on the previous side here. We were identifying degrees of these standard form polynomials, and we did that by looking for the highest exponent on a variable here, right? That determined the degree. Well, what about if we have something in factored or intercept form? How do we determine the degree? It is not 1. We do not look for the highest exponent on a variable here, right, which would be 1. Each of these has a 1. But if we multiplied this out and got in standard form, the exponent on x is not going to be 1. So let's actually multiply it out and see what we get here. So we have 3 binomials, and in order to multiply this out, we'll have to FOIL these out. Doesn't really matter what order we do it in. I guess I'll just do the first 2 binomials first. So we're going to do x times x, which is x squared. X times 1 is 1x, or just x. 3 times x is 3x. 3 times 1 is 3. I'm going to keep that in parentheses because it's still multiplied by this x minus 2. And then I can simplify. I should be writing smaller here. I'm going to run out of room. All right, so we have this. And now I need to multiply those together. So this isn't exactly FOIL, but it's the same idea. I have to multiply each of these by each of these. So x squared times x is x to the third. X squared times negative 2 is negative 2x squared. 4x times x is 4x squared. 4x times negative 2 is negative 8x. 3 times x is 3x. 3 times negative 2 is negative 6. And then I can combine like terms. I'm going to try to squeeze that in over here, my final answer. So I get x to the third plus 2x to the second minus 5x minus 6. Okay, now we can see the degree is 3, but man, that was a pain to multiply that all out. So yeah, is there a shortcut to determine the degree of a polynomial? Well, let's revisit that original polynomial again. And instead of multiplying it out, which that took some time, is there a way we could determine the degree? Well, we can kind of think about, notice how we ended up with an exponent of 3, and we had 3 x's here. So it's really the amount of x's you have. So we have 1, 2, 3 x's, okay? 3 x's. So that means the degree is 3. Now you got to be a little careful here. What if we have this situation where we have an exponent of 2 on one of the factors here? We call each of these binomials, we could call those factors also. Yeah, this would definitely take a long time to multiply this all out. We're not going to do that. So we're going to use this shortcut to determine the degree. So what we do is we just count up the number of x's, 1, 2, 3, 4, 5. However, I did that wrong on purpose. We actually have 6 because this counts as 2. I mean, if you think about it, if we expanded this out just a little bit, we're not going to do the full expansion. But really what x minus 1 squared is, it's 2x minus 1s being multiplied, right? So really we have 6 x's, 1, 2, 3, 4, 5, 6. So the degree is, oops, can't see that. There we go. The degree is 6. All right. And yeah, you could even avoid doing this. You could just kind of go 1, 2, 3, 4, 5, and count this twice because you see that exponent of 2, 6. So 1, 2, 3, 4, 5, 6. All right, and that gets